Okay, so I will do it in English mostly because even if I try in French, half of the words would have to be in English for me. So I just keep it 100% like this. But at the end, feel free to ask questions in French. Um, so I will be talking about the prediction of livability in urban areas using deep learning and aerial images. So the semantic intermediate concept is something I will explain briefly, but it's not really like the main aspect of this work that I have done together with like our PhD student Alex Levering, who is doing his PhD in Wageningen University in the Netherlands, Jasper van Vliet, who is in Amsterdam, and Davis Theia at EPFL in Switzerland. So maybe the first thing is just, okay, what is urban livability? And so the definition that we found is like the degree to which its provisions and requirements fit with the needs and capacities of its members. So it refers to urban areas. So it's like to what extent urban areas provide inhabitants of these urban areas what they need. And so we started working on this because the Dutch government has a survey that lately has been performed around every 2 years. So in the beginning it was a bit more. So it's a survey in which they go to like thousands of households in the whole country, and they ask about how they feel that their needs are covered by their urban environment, and then they try to link these responses from the survey to like over 100 explanatory variables, and these explanatory variables range from like the more like geometric aspects of the urban space, like the size of the streets, the distance to green areas, the surface of green areas, whether there are supermarkets around or not, distance to the closest train station, like a bunch of things that determine the quality of the urban space. And so this is an effort that the Dutch government pays lately every 2 years. And they get maps like this, in which for every postal code of the Netherlands, you have like a certain score of like how livable is it according to its inhabitants. And on top of that, they sort of try to like a posteriori. So they in the survey they get like an idea of the general livability that inhabitants perceive, and then a posteriori they try to split this score into 5 sub-scores that relate to a different subset of these 100 explanatory variables. And so they are grouped in these 5 buildings is more related to like the quality of the buildings, the time they were built in, the type of buildings and so on. The physical environment relates mostly to green areas, but also access to nature. Amenities relate more to distance to train stations, to hospitals, things like this. Population is like they have some demographic variables in there, and safety is more like reported crime or perception of crime and things like this. And our idea was, okay, like this effort has already been done and is being done more or less recurrently. But our question was, can we sort of interpolate over these scores, over these surveys, using aerial imagery and deep learning methods? So the first thing we did is to basically match these 2 data sets. On the one hand, this LEV barometer, so this information about the livability, including the 5 domain scores and the final score, together with an aerial image. So the Dutch government also has like every 2 years again, like flight campaigns where they basically take like an aerial imagery of the whole country. So we just matched these 2 data sets together in a way that, so basically we took like image patches of 500 meters times 500 meters, because it's kind of a compromise between like the things that that can be sort of accounted for in these scores. So some of them are not. So typically, distance to the closest hospital often is more than the 200-meter radius that this type of image provides. So these kind of aspects will not be captured, but many others like direct access to green spaces or type of buildings can be captured by this type of imagery. So based on that, we chose 9 cities in the Netherlands to be used for training the models and to validate them. So like within each city, we randomly took some squares out to use for validation. And in addition, we chose like 4 other cities to use for testing to see, okay, like the deep learning models that we can train on some cities, do they also generalize to a different set of cities, I mean, always within the same country? And so the type of model that we learned, it's based like on a standard convolutional neural network. So there we didn't do anything particular. But then we had a structure in which this convolutional neural network was trained to take in an aerial image patch and then produce a set of these 5 intermediate scores, which are then linearly combined in order to obtain the final livability score. So like this, there are these 2 types of outputs that the model was trained on simultaneously. And so what we found first is that training a model in this way, so this is what we call bottleneck, does not result in worse results. It actually improves the results a little bit. So here, so this is the R square on the test, on the validation and the test sets. And we can see that the bottleneck tends to provide like substantially higher results on the validation sets. So we could imagine that maybe there is some overfitting going on. But if we look at the test cities, so the cities that were really like not seen at all during training, we see that both models produce more or less the same result in terms of the final livability. So like predicting these intermediate 5 scores doesn't result in a degradation of the results, but actually like a slight improvement. Also what we saw, so these are the 4 cities in the test set. And we see that so Dordrecht and Eindhoven are 2 cities that are quite representative of the Netherlands, and therefore they're probably more similar to the training set. And in general, most of the scores have like relatively high numbers, like quite acceptable in terms of the R-square scores. But then, for instance, Basel is a lot smaller than any of the other cities that it was trained on. So like we see that most of the scores are substantially lower, and in particular the amenities, so like this distance to hospitals, distance to a train station, is basically 0. So it's not able to generalize at all with respect to that, which is also not a surprise given that it often captures aspects that cannot be seen within the image patch. Also Hengelo is a bit more of a representative city in the Netherlands, but it's geographically more isolated than all of the others. And in that case, we also see that some of the scores suffer from that. And it's basically all of the scores are slightly lower than in most of the cases up here. Then in terms of these individual intermediate scores, what we see mostly is that, again, this amenities score, so like if we look at the scores, so in terms of R-square and Kendall's tau, which is like another metric of correlation, what we see is that in the validation set, so this is checking the score on different patches of the same cities that the model was trained on, it basically always gets like pretty high results. So all of the scores basically work. So we can use the this type of approach to predict the scores in other parts of the cities where we already have data. This is more or less what we can get. But when we move to the test set, and this is the score change when we check the test set, we see that mostly, again, these amenities is what suffers the most. So like so this score here is probably just an overfitting to the training set, and the huge drop in the score suggests that this doesn't generalize to new cities at all. And however, the one that does generalize the best is also, not surprisingly, the buildings score. And after all, like the building score really talks about something that can be more easily seen on aerial images. So this is also no surprise. So if we look at the results more visually, so this is for Eindhoven, which is a quite representative city. So we see that between the ground truth and the prediction, so the spatial patterns that emerge are quite similar. So we can see that more or less the same areas of the city correspond in both images to low and high values of this building score aspect of the livability. In cities that are a bit less representative, like Hengelo, we can see that the general patterns sort of do correspond, but the model misses like particular hotspots of low building score in some areas of the city. So like the more extreme cases are basically missed. And if we move to even farther away to a small city like Basel, the model basically completely fails. And so in the case of the amenities score, the ground truth says that, okay, like this place is very isolated, it's very far away from basically everything, and this is not something that the model has been able to capture, simply because it cannot see it on the images. So as a conclusion, we have seen that remote sensing and deep learning can indeed be used to estimate at least some aspects of urban livability, but that only physical aspects can be really extrapolated to new cities. And also this extrapolation only works when cities have a relatively similar structure to those the model has seen during training. So if you have any questions.